This is a video for AQA Further Pure, second order differential equations 2, non-homogeneous equations, 2.3, particular integrals, polynomials. We've seen in previous videos how to solve this type of non-homogeneous differential equation by looking first of all at the homogeneous version and finding the complementary function. We can then find the particular integral by substituting something of the same form as this right-hand function fx. The general solution is then the sum of the complementary function and the particular integral. Let's have a look at this example. This shape of differential equation, the homogeneous type, we have seen before and have solved for the complementary function. And that complementary function is y is equal to ae to the 2x plus b to the minus x. In this example, I've got a right-hand side of 3x squared plus 7x plus 1. And I want to work out what kind of particular integral I want to complete the general solution for this. I'm going to try y is equal to ax squared plus bx plus c. That's going to give me a first derivative, dy by dx, of 2ax plus b, and a second derivative, dy by dx squared, of 2a. Now if I plug these bits in to the left-hand side, I'm going to get 2a minus 2ax plus b minus 2 lots of ax squared plus bx plus c. And that I want to be equal to 3x squared plus 7x plus 1. So I'm going to look at the coefficients on both sides. And if I start by looking at the x squared coefficients, well, on this side I've just got minus 2a, and on this side I've got 3. So that's going to tell me that a is equal to minus 3 over 2. If I look at the x's now, I've got a minus 2a from the first bit here, and a minus 2b from the second bit here. And that's going to be equal to 7. But I already know that a is minus 3 over 2, so this is going to give me 3 minus 2b is equal to 7, and this tells me that b is equal to minus 2. And if we now look at the constant terms, I'm going to get 2a minus b from the middle bit and a minus 2c from the last bit, and that's got to be equal to 1. And again, I already know that a is minus 3 over 2 and b is minus 2, so I'm going to get minus 3 plus 2 minus 2c is equal to 1. Well, this gives me minus 2c is equal to 2, so that gives me c equals minus 1. So my particular integral is going to be y is equal to minus 3 over 2 x squared minus 2x minus 1. Okay, there's that written up neatly for you. It's quite compact, this, so we'll take a bit of time taking this apart. There's the original question at the top. For the particular integral, we tried something that is the same shape as this. I've got some x squared, some x's, and a constant, so I've tried that. Here is where I've differentiated those two to give me 2ax plus b and 2a. And then substituting in to the original differential equation, I get this thing here. So here I go through comparing coefficients. From x squareds, I get a value for a. From the x terms, I can deduce a value for b, and from the constant terms, I can deduce a value for c. And I get my particular integral as we identified on the previous slide. Okay, so now we just have to put everything together. Here's my original differential equation. We were actually given the complementary function, but we have worked this out before. We've now found the particular integral here, and so the general solution is the complementary function plus the particular integral. There's a plot of a couple of versions of that. This is the general solution, and here's a plot with a equals 0.3 and b equals 0.3. And you can see we get this shape of curve. The intercept here, well, that will occur when x equals 0, and if we just think about what we've got up here, so if x equals 0, we're going to get that y is equal to a plus b minus 1. If you look at this, that's going to be 1, that's going to be 1. These two are going to disappear. And for this example then, this is going to be 0.6 take away 1 about minus 0.4, which looks right. In this example where a and b are 1, this is going to give me an intercept of 1, and that looks to be right as well. Now the other thing to notice is what happens for behavior for large x. Provided a and b are non-zero, then for large x and positive, so as x tends to infinity, we're going to get that y tends to infinity provided a is not equal to 0. If a is equal to 0, we need to have another look at that and see what happens. As x tends to minus infinity, y is also going to tend to infinity, provided that b is not equal to 0. And again, we'll have a look in a second at what happens as we change the parameters. So let's have a look at a dynamic plot for that. You can see that this has the same parameters as this graph over here. Okay, let's have a look at what happens. I said that when a equals 0, things get more interesting. Well, when a is equal to 0, instead of y shooting off towards infinity, it's going to shoot off down here to minus infinity. And actually it's tracking this curve here. And this curve is the minus 1.5x squared thing. Let's look at what happens if b is equal to 0. So if b is equal to 0, again, it's going to track the minus 1.5x squared thing. So to summarize what we've found out so far, if the right-hand side, the fx in our differential equation is a linear function, we try ax plus b as our function. And if it's a polynomial, although we've only looked at a quadratic, it does actually work for polynomials. If it's a polynomial, we'll try a polynomial of the same order. The next video in this sequence is 2.4, Particular Integrals, Trigonometric Functions.